Hello everyone, we move on to tutorial number 18 of IIT-JAM in chemistry, and this is lecture number 4 of the physical chemistry chapter gaseous state, and the topic right now going to be discussed is Maxwell Boltzmann distribution on molecular velocities. So let's start with the probability distribution curve. Gaseous molecules at a certain temperature have different speeds ranging from 0 to very high values. Total number of molecules in a certain volume is actually the number density, which is denoted as n prime. The number of molecules having speeds between c and c plus dc. So velocity from c to c plus dc, and within this range the number of molecules is dn suffixed c. The fraction of the molecules having speeds between c and c plus dc, that is, if this is the total number of molecule, then if this is the number of molecules within this velocity, then what is the fraction? Definitely its ratio, that is dnc over n prime. Now if m is the mass of each gas molecule, then the probability of finding the molecules having speeds between c and c plus dc, and this expression has been derived by Maxwell and Boltzmann, and thus from the graphical presentation of this expression we get the probability distribution curve, and this probability is denoted as Pc, and this is the ratio dnc by n prime. When divided by dc, then Pc is obtained. That is a very small range of speed here. So this is the fraction dnc by n prime, then divide this by dc. So actually it becomes 1 over n prime, then dnc by dc. So this is the probability of finding the molecules having speeds between c and c plus dc. And the expression as derived by Maxwell and Boltzmann, it is 4 pi within bracket m by twice pi kt whole to the power 3 by 2, then exponential minus mc square by twice kt c square, and this is denoted as equation number 23 as continuation from the previous lectures. Here Pc is the fraction of the molecules having speeds between c and c plus dc per unit interval of speed, and if we look back to this equation number 23, then we find that all these parameters except temperature and c are constants, where c and t are the variables. Therefore, we can conclude that Pc is a function of temperature and molecular speed. And the curve obtained from the graphical plot of Pc against c is the probability distribution curve, and this is asymptotic in nature. And this is the curve here, steep uprising, then down falling a little less steeper way. Here in this point number 1, the most number of molecules having some velocity, and this is definitely not equal to the average velocity. The position of average velocity here, number 2. And what about the RMS velocity? It is much further in the right position here. This is the position of the RMS velocity. And this number 1 is a new category of velocity apart from c bar and ca. This is the third category of velocity. We haven't mentioned about that until now. Now we are just getting this third category of velocity. This is denoted as CMP and known as the most probable velocity, and it has something different expression. It is root over twice kt by m or root over twice rt by m. Now this asymptotic curve is constant, is a particular curve at a constant temperature. Now if temperature is not kept constant, it is changed from higher temperature to lower temperature or lower to higher temperature, then the nature of this curve little bit changes, and the most probability velocity shifts to the right hand side with increasing temperature and to the left hand side with decreasing temperature, and at absolute zero it gets narrower, narrower and narrower. This way the definition of temperature is also obtained from the kinetic theory of gas. Here if this is temperature T1, then T1 is the highest temperature and the curve has the highest widening, while this is T4, this has the lowest temperature and it is the narrowest among these 4 curves here. So this is temperature dependence of the probability distribution curve. And here is the expression of the most probable velocity, the third category of velocity, and it is root over twice kt by small m or root over twice rt by capital M, and this is denoted as equation number 24. And the curve narrows on cooling and widens on heating, as I have mentioned here during the discussion of this graphical presentation. Therefore, we find that the most probable velocity is greater than Pc at Ca greater than Pc at C bar. That means the order is C bar is greater than Ca is greater than Mp. Okay, so this is the order of the velocities. That means this is highest value, but this is having the lowest number of probability, isn't it? That is, Pc at most probable is highest, where Pc at RMS is lowest, whereas the value of C bar is highest while the value of Cmp is lowest. So this is Pc at Cmp, this is greater than Pc at Ca, this is greater than Pc at C bar. So the number of molecules having the RMS velocity is lowest in comparison to the number of molecules having the average velocity, and in further comparison to the number of molecules at Cmp. This is Mp, that is the most probable number of molecules are occupying here. But the velocity is in the reversed order. That is, this one has the highest velocity. It is root over 3 kt by small m. This is root over 8 kt by pi small m, and this is root over twice kt by small m. The velocity distribution curve for different molecules, if m is changed in the equation number 23, m has been taken to be constant for a particular gas. But if you take different types of gases, then you will find that this curve will widen with decreasing molecular weight. So if the molecular weight increases, then the curve gets narrower, and if the molecular weight decreases, then the curve gets wider. So oxygen is the narrowest, and then it is less narrower. It is more narrower than nitrogen. It is narrower than water. Water is narrower than helium, and helium is narrower than hydrogen at a particular temperature. That is, heavier the molecule, narrower the curve at the same temperature. So that's all about the velocity distribution curve and the Maxwell Boltzmann distribution. Now move on to the questions. This question came in IIT-JAM 2007, and repeatedly it came in 2011 also. And the question is, the Maxwell distribution function for the distribution of speeds of molecules in gaseous system is given by this one. Definitely that is the equation number 23, and the most probable speed is, and just we have derived the expression of most probable speed, and that is root over twice kt by m. This one, root over twice kt by m. So the correct option is this one. So this is the correct answer. Move on to the next question. This came in 2008 JAM. Given that the most probable speed of oxygen is 1000 meter per second, and the mean or average speed in meter per second under the same condition is what? So let's find the answer here. So the ratio of most probable speed and average speed according to the expressions is root over twice kt by pi m divided by root over 8 kt by pi m. Root over twice kt by m divided by root over 8 kt by pi m, and it is nothing but root pi by 2. Therefore, Ca equals to what? Ca equals to Cmp by this ratio. So Cmp divided by this ratio. So it is Cmp divided by root pi by 2, that is 2 Cmp by root pi. And the value of Cmp is given by, it is given here 1000 meter per second. So just put the value 1000 and get the, after calculating, get this result 1128.38 and approximate it to 1128 meter per second. So the right answer is option B is the correct answer. Now question number 11. This came in 2011 JAM, and here instead of C, V term is used. All are same. So the Bmp means the most probable velocity. It is root over twice RT by capital M. So here the value of R is taken to be 8 joule per Kelvin per mole, you have to calculate the most probable velocity for methane gas at 127 degree Celsius. What about the answer? Temperature is 127 degrees Celsius, that means 400 Kelvin, and the molar mass of methane in the SI unit is 0.016 kg per mole. Therefore, in the expression of BMP, we just put these values. In place of R, we are putting 8. In place of T, we are putting 400, and in place of M, we are putting 0.016, and this way we get the answer 632.46 meter per second. From the kinetic theory of gases, the ratio of most probable speed to the RMS speed is what? This question came in 2016. So several options are here, and the correct ratio is root over 2 by 3. That means root 2 by root 3. Therefore, option B is the correct answer. Just simply take the ratio root over twice kt by m by root over thrice kt by m. Next question number 13. This came in 2022. The Maxwell Boltzmann distribution function of Vx, that means function of Cx, of one-dimensional velocity. One-dimensional velocity we didn't discuss. So just for your convenience, we are just mentioning it here. One-dimensionally, the velocity is a e to the power minus mc square cx square by twice kt. So here in place of cx we are writing vx, and in place of Boltzmann constant k we are writing here kb. All are same. So therefore the correct option is A here. It matches with A. And next question. This came in 2015. In an ideal monatomic gas, the speed of sound is given by root over 5 RT by 3m. If the speed of sound in argon at 25 degrees Celsius is 1245 km per hour, the root mean square velocity in meter per second is what? So it's very easy question, because speed of sound, we have to convert this into the SI unit like this. So kilometer into 1000 and per hour into 3600. So in order to get it in the meter per second unit, so it is 345.83 meter per second. Now the ratio of speed of sound over CRMS, that is the ratio of sound and CRMS, is the ratio of their expressions. So here is the expression of sound, speed of sound, so root over 5 RT by 3m as given in this question here, and we know the expression of CRMS, it is root over 3 RT by capital M, and the result is root over 5 by 3. Therefore, what is the value of CRMS? CRMS should be speed of sound divided by this ratio, that is root over 5 by 3. Therefore, CRMS equal to speed of sound divided by root over 5 by 3, that is 3 into speed of sound divided by root over 5. So it is 3 into the result obtained here in the SI unit, 345.83 divided by root 5, and the value is 463.98 meter per second, approximated to be 464 meter per second. So that's all about this lecture. Thank you. Have a nice day.